Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. So we are going to start with matching with lump elements or L section network. So there are two configurations can be considered, but it dependent on the impedance, the characteristic impedance of the system. So if the characteristic impedance lies within the 1 plus jx section, so the left hand side will be chosen, or else if it is outside the 1 plus jx section, then the circuit B will be considered. Okay, brief information on the L section network. So it is one of the simplest matching network that uses two reactive elements which are the Jx and also Jb, the susceptance and also the reactance, to match an arbitrary load impedance to a transmission line. And the reactive elements may be either inductors or capacitors or combination of both, and it depending on the load impedance you have. So the first decision that you need to do is to choose whether to use the A configuration or B. So it dependent on the normalized load impedance. Alright, so either the normalized load impedance is inside 1 plus jx circle of this on the Smith chart, or it is outside. If it is inside the 1 plus jx circle, so this is your Smith chart. So 1 plus jx is here. Okay, so if the normalized load impedance lies within this area, so you will be using configuration A, or else if it lies outside the 1 plus jx circle, so you need to use the configuration B. Okay, in terms of the lump elements inside the reactance or susceptance circuit, so if you compare this one is JB and JX. B is the admittance, okay, the susceptance, and X is the reactance value, right? If you have the normalized load inside 1 plus JX circle, so you'll be using this circuit. So what will be the component of JX and JB? So it depends on the value of your susceptance and also the reactance. All right, so from Delft's formula, if you have the susceptance B is negative, okay, so for the first element that you need to look at is the, for example, for configuration A, so the first one you will be seeing the component of the first element here, and next will be here. Alright, so since the first component is in parallel to the load, so we'll be considering the admittance or the Y chart. Okay, so next we need to convert it into the Z chart, the impedance chart, so that we can get the X. Okay, if since we are using the Z chart, so we need to transform, or you need to rotate the impedance chart to indicate the the admittance, right? So this is the reflection, the Smith chart. So you have the 1 plus jx for admittance here. So to use this, the same chart as the admittance circle 1 plus jx, jb, it will be, you need to draw another one here, so 1 plus jb, so this representing the susceptance, and here 1 plus jx. Okay, but it will be good if and usually people will be using the other types of Smith chart, the ZY Smith chart, which include both the admittance and also the susceptance, or the impedance and also the admittance within the same chart, but will be a bit more messy, a bit more complicated, since we have been using the Z chart from the beginning. So we'll be using Z chart as well in this topic. All right, so in terms of the element, so if you have the B, okay, from here, if you get the B is positive, maybe somewhere here, so then the component here will be capacitance, and the equation to get the capacitance value is as shown. All right, if you get the B is negative, okay, maybe somewhere down there, then the component at this point is the L, the inductance, and you can calculate the value of the inductor by using the equation. Okay, next, once we have solved the B, then we look at the second component in series, which are the JX. So then you need to refer to the Z lines within the Smith chart, right? So when X is negative, somewhere down here, so the component that you need to use at this point is the L, and if it is positive value, then you need to use when it is positive, it is L. If it is negative, it is C. If it is negative, then the component here will be C. Okay, same goes to the other configuration. Okay, however, in this case, the normalized load impedance will be outside the 1 plus JX circle. So what's the difference between the smaller, the capital letter B, and also the smaller b? So the smaller b, basically the normalized values that you got from your Smith chart, but here is the real value that you have multiplied by the Z naught. Okay, this slide summarizes the components that may be included in the matching circuit if you have different X and B values. All right, so the right hand side here representing the 1 plus JX, and the other side is 1 plus JB. Okay, let's look at an example, designing an L section matching network to a series of R and C load with an impedance of load impedance of 200 minus J100 ohm to a 100 line, meaning that the characteristic impedance is not equal to 100 ohm at a frequency of 500 megahertz. All right, so as usual, to perform matching networks, it will be much easier to use the Smith chart. Okay, so let's have our Smith chart in hand. So as mentioned earlier, for L section, it will be much easier if you use the ZY combination chart. However, since we have been focusing on the Z chart from the beginning, so we are going to use the Z chart in this solution. However, there will be a bit more steps so that you can translate the Z into Y to get the shunt component solved using the Z chart. Okay, let's have the first step. As usual, you need to find the normalized load impedance. So given the impedance is 200 minus J100, so divide by the Z naught equal to 100 ohm, so you get 2 minus J1 plot. So plot it in the Smith chart. So that's your JL2 intersect with minus J1. Okay, and then you need to look at whether the ZL lies within the 1 plus JX or not, then you plot the 1 plus JX and the admittance 1 plus JB. Alright, so this is your 1 plus JX circle, and the other one is 1 plus JB. Okay, once you have this, so obviously the ZL lies within the 1 plus JX. So if it is 1 plus JX within the 1 plus JX circle, so you need to use the configuration A, in which you have the JB component in parallel. So the first element that you need to analyze is the JB in parallel to ZL, and the second component will be the series one. So since JB is in parallel to ZL, so it is a shunt configuration, so you need to use the admittance circle to solve for the component's value. Right, so in order to have the admittance, so as discussed earlier, so the admittance is basically the translation or the opposite of your ZL. So you draw your SWR circle and get your admittance YL. Okay, so your YL in this case is 0.38 plus G02. Alright, so next you need to perform matching the YL position to the match 1 plus JB circle. So in order to do this, you have two solutions. The first one is whether you move this point up. So you need to maintain the same real part, 0.38. So either it is here, okay, move it there, or you can also move downward. Okay, move downwards there. Okay, we can call this solution 1 and solution 2. Okay, so let's take a look at the possible solution. So to match the admittance to 1 plus JB, there are two solutions. So the first one, so we take a look at the shortest distance. So we move YL to position 1. Okay, position 1 is up there. So that's the shortest. Okay. So we name it as YL1. So the location is at 0.38 plus G0.48, 0.48. All right. So that's solution 1. So to get the B, okay, what's the B? Is the difference between the original position to the latest position. Okay, the difference is whether you move the YL upwards or downwards. So in this case, it be moving upwards, so it's positive configuration. Positive by how much you move it? So by positive 0.28. All right, original position is at 0.2. Originally at 0.2, you move it up to 0.48. So the B is positive 0.28. Right, so the next possible solution is to move the YL downwards, so YL2 down here. So when it is been moving downwards, so obviously the J will be negative. Okay, the movement is in negative order. So how much? From 0.2 up to this point. This point is 0. minus 0.48. Okay, so the possible solution is B2 equal to, so the total movement is 0.2 plus 0.48, 0.68 in downward. Okay, downward, so it's negative. All right, from the positive P and negative P, then you can decide which component to be used, whether it is inductor or capacitor. So the first element, so the first element here, depending on the B. All right, so let's go to the table again. Okay, if we have we start with the solution 1. So if we have B is positive value, so B is positive, so the component will be at this point is the C. Okay, so what will be the C value? You'll be using this equation. Okay, C B, you have positive 0.28, and Z0 is 100, F is 500 megahertz. So we get your capacitance value. Okay, so in this case, the capacitance value for this position is 0.89 picofarad. Alright, so next, to get the series component, so you have solved the this one. So now you are going to look at this. So Jx is in series, so you need to translate this, the first solution just now, to be intersected with the 1 plus jx circle. So 1 plus jx circle is there, so you need to translate this point to 1 plus jx circle. Okay, so you draw a line crossing at the center, and then look at the cross section between the lines to 1 plus jx circle. So you can name it as ZL1. So in this case, ZL1 is positioned at 1 minus J 1.3. Okay, so then to know what components will be in there, so you need to look at the x value. So the x value is not directly the value there, so you need to look at what will be the x if you want to match this to 0 position. Okay, to remove the, or to eliminate the imaginary part, so you need to introduce plus J 1.3. Okay, so because here is negative 1.3, so to cancel this out, you need to introduce plus J 0.3. Therefore, your x will be plus J 1.3. So plus J, refer again to the table. Okay, if J is positive, if x is positive, so you'll be having L, okay, with that equation, so you can calculate your L values. So in this case, your L will be an inductor with 41.4 nanohertz. Okay, so that will be your final circuit for solution 1. Okay, same goes to solution 2. Okay, if you are going to use solution 2, then we have calculated the B2 just now. Okay, so you refer to B2. So in this case, B2 equal to negative J equal 0.68. So refer to the table whether if B is negative, what will be the component in here. Okay, I suppose it will be the inductor in this case, in the second case, in the second solution. Then you need to translate, to get the series, you need to translate this one, draw a line crossing at the center, and then look at the intersection at the 1 plus jx. Okay, we can call it ZL2. So example, so you can draw this properly and get the value. I suppose that it's supposed to be plus jx 1 plus j 1.3 or 2 or something. All right, and then this is the current position of ZL. To get it matched, you need to remove, to eliminate the imaginary part, so you need to introduce negative J 1.3. So your x for second solution, x2, will be negative. So then refer to the table again. If x2 is negative, then what will be the component and what will be the value. Okay, so after both consideration, so this is solution 1 and this is solution 2. Okay, so for solution 1, okay, please recheck again the value. This is the one from the reference book. So but when we refer to the Smith chart, there will be some differences in terms of the value, maybe just plus minus 2 to 5 points. So should be okay as it is within range. So you'll get the C and L different configuration, but the same concept. When you have the normalized impedance within the 1 plus jx circle, so the configuration will be jx series, and then you have the first element jb will be in parallel to the load zl. Okay, so it doesn't matter whether it's capacitor or inductor, but then there's just calculation. All right, there's a rules that you need to follow in order to get the system match, right? If you are plotting the reflection coefficient, solution 2 seems to be better match at higher frequency. So we can look at this when we perform the simulation using simulation software. Okay, next we are going to look at another types of impedance tuning technique, which is using quarter wave transformer, or by inclusion of additional λ/4 element in between the transmission line and also the load impedance. Okay, so how the quarter wave transformer looks like. So basically additional element of λ/4. Okay, this part being included in between the input point or the generator and the load. Okay, normally we have seen this, the generator, and then we have the transmission line terminated by load impedance. Okay, all right, so we have seen earlier to match the ZL to Z0. So we have Z0, the transmission line characteristic impedance. So to match ZL to Z0, we can use the stub matching technique. We can also use the impedance matching or L section matching techniques. And so now we are going to look at another technique that can be used to match the Z0 to the ZL2, the characteristic impedance, by the inclusion of additional element by the length of λ/4. Right, so the characteristic impedance for the additional λ/4 element is given by Z1 equal to Z0 ZL square root. So in which basically the load must match to the characteristic impedance of the earlier or the prior element, and then Z1 need to be matched to the original or the real impedance of Z0. Okay, so the characteristic impedance of the quarter wave transformer or λ/4 transmission line is equal to Z0. So in this case, the Z0 is in this case it's 50 ohm, and the ZL is the value here. Okay, and what else here? All right, so the advantages of using the quarter wave transformer is it can be extended to multi-section designs. Therefore, it can provide broader bandwidth. Right, if just narrower bandwidth needed, so the designer can simply use single section transformer. Alright, so this figure basically shows the single section transformer in which only one λ/4 element is included into the design. However, the drawbacks of the quarter wave transformer techniques in which you need to cut. Okay, for example, you have a transmission line and a load, and if you want to include the λ/4 element, so you need to cut the original structure and then add in the λ/4 element in between. Alright, therefore the modification may affect the frequency of operation, and the other drawbacks is the system can only match to real load. Okay, so it will be difficult for complex load. And another important parameter that you need to consider in designing a quarter wave transformer. So the first one will be the reflection coefficient. Maximum meaning you are using the maximum SWR, so in which we know that the reflection coefficient can be calculated by the SWR minus 1 divided by SWR plus 1. Okay, alright, next we can estimate the bandwidth, the percentage of bandwidth that can be provided by the system by using the following equation. Okay, this slide shows how the signal or the power travels along the transmission line when you have additional section of quarter wavelength element in between the input and also the load impedance. So this is the first intersection between the input point to the lambda over 4 element. Okay, and another intersection towards the load. So what happens when you have the signal or the input being injected into the lines? So there will be reflection at the intersection point, at this point. So the reflection being given by reflection coefficient 1 or gamma 1, and then besides the reflected signal, there's also transmitted signal from the first element to the second element. This is the transmittance or the transmitted signal from point 1 to point 2. All right, and the signal travels along the lambda over 4 element, and then there's another intersection. So there's another reflection at this intersection, so given by reflection coefficient 3. Okay, this is the third point. All right, so and then some of it will be transmitted from 2 to 3. Okay, this is from 1 to 2. Okay, and then so you can see that the reflection coefficient and the transmittance value very dependent to the element connected to it. Right, so the reflection coefficient and transmittance from one section to another can be estimated by the following equations that dependent on the characteristic impedance or the impedance at each element. So Z1 at the earlier point, okay, or at the transmission line 1, and then Z2 in inside the element 2, and etc. Okay, let's look at an example. Design a single section quarter wavelength matching transformer to match a 10 ohm load to a 50 ohm line. Right, so we have 50 ohm lines, Z0 equal to 50 ohm, and then we have a quarter wavelength lines lambda over 4 to match a 10 ohm load. Okay, so now it goes into the load. ZL equal to 10 ohm. So the frequency of operation is 3 gigahertz. So the question asks you to determine the bandwidth, percentage of bandwidth that can be provided by the designed matching transformer. Okay, so in order to get the bandwidth, you need to have the reflection coefficient. All right, so given the SWR is 1.5 maximum, okay, it could be less or equal to 1.5. So assuming that the system is using the maximum value of SWR 1.5. So the maximum reflection coefficient can be calculated by SWR minus 1 divided by SWR plus 1. So the reflection coefficient maximum is 0.2. Then you can use this value to calculate the bandwidth. Okay, fractional bandwidth is given by this equation. So it dependent on the reflection coefficient maximum that we have calculated earlier. So, and then your ZL given as 50 ohm, and then Z2 is the load. Okay, it's 10. So, and then you have the reflection coefficient, then you can get the fractional bandwidth. And since the question asks you in percentage, so make sure you give it in percentage. So 29% of bandwidth can be provided by this design. Alright, so the figure shows the multi-section transformers. Okay, it can be a step transformer, it could be within the cable as well. In terms of the microstrip antenna designed, and this one of the converter that, if you can see the value here, 50 to 70 ohm converter. So it depends on the targeted output or targeted application that need to use this type of conversion or matching. Right, so another one is the step impedance in microstrip lines. So if you have a multi-band signals, or if you want to achieve broader bandwidth for a transmission system, therefore this kind of matching technique can be implemented. With that, thank you.